All right, here we go. Before we start doing anything with new material, I want to just do a quick little reminder about the most important thing from class last time, and that is the most important thing about probability. I'm sure that you're all very comfortable with this idea, but I just want to remind you, probability is always going to be successes over outcomes. How many successes are there? How many outcomes are there? And that's how we're going to find our probability. Make sure you keep that in mind as you're working on problems from this entire week and as we go forward a little bit in section 7.4 in future weeks. Probability from a table. So we might be given a bunch of information in a table and we're supposed to find probability based on that information. So data from a recent 5K run for charity were compiled, and we have adults and children were involved in this 5K run, and we had some people that ran and some people that walked. And they're all broken down into those categories of adults, children, people who ran, people who walked. We can see it all in the table right there. And if our job here is to pick one person at random, so we have everybody's name in a hat, we're going to reach in, pick out one name at random, and the question is find the probability that the person chosen at random is an adult. So what we're after here is the probability of picking an adult at random. Just like every other probability question, this is about successes over outcomes. So let's see, how many outcomes do we have here? Well, as I look at my chart, there's 23 plus 11 plus 14 plus 22. I need to add all of those together if I'm going to find out the total number of people who were involved here. So I'll just add all those together. And let's see, 23 plus 11 plus 14 plus 22. Looks like I have, 23 plus 11 plus 14 plus 22. There we go. 70 total outcomes. Let me know if you don't see where those 70 outcomes came from. My denominator here is going to be 70, and now I just have to find my successes. And my successes here are the people that are adults. So let's see, I have 23 adults that ran, I have 14 adults that walked, so altogether I have 37 adults. So I have 37 successes out of my 70 outcomes. The probability of picking an adult will be 37 out of 70. Again, successes over outcomes, and we just use the table to help us find that probability. Let me know if you have questions on this before I have you try one. All right, here goes. Same data from this 5K run that we were talking about in the last problem. And then my question for you in this one is find the probability that a person chosen at random is somebody who walked. I'll set up a poll and let you try it. And keep in mind the idea here is within that problem, we're choosing one person at random from the group. So it's very similar to having an entire deck of cards. They all get mixed up and we pick one at random. This is a similar idea. We have all the names in a hat. They all get mixed up and we pick one out at random. And the key here is just like any other probability question, we're looking for successes and outcomes. Go another 30 seconds on this and then we'll talk through it together. All right, let's see what we've got for this one. Unanimous. Excellent. Still don't like the way those poll results are, but I'm going to try to complain less about the new revised big blue button than I did last time. All right. So this one was unanimous. So what that means is we are going to be able to go through this one pretty quickly. So as we look at this one, we're going to have the question we're being asked. And if things take me a little longer, it's because I have to hit a lot more buttons with this revised big blue button. I'm not going to complain about it. It's just going to take me a little longer. So here we want the probability that a person chosen at random walked. So we want the probability that one person walked. We know from before that there are 70 outcomes, so that's going to be our denominator. Now we just have to find the people who walked. And that's going to be these people here. Adding those together, we have 36 people who walked. So the probability that somebody walked is 36 out of 70. You could reduce that, I guess, to what, 18 over 35 if you wanted to, but you don't have to. 36 out of 70 would be just fine. Let me know if you have any questions on that. That's basically the idea behind probability from tables. Odds. Odds is a new idea for us, and it's very much related to probability, but not exactly the same thing. So when we talk about odds, one of the things I want to make sure that you're comfortable with is that we're going to write odds differently than we write probabilities. Odds are going to be written as a ratio with a colon between the numbers. And perhaps more important than that, we are not going to write odds as a fraction. So if you're asked for odds, you're definitely not going to write it as a fraction. There are books out there that do write odds as a fraction. I don't like that though, because then it's easy to get confused between, well, is this supposed to be odds or is this supposed to be probability? That's not going to be an issue for us, because if it's a fraction, we know it's a probability, and if it's odds, we are not going to write it as a fraction. Instead, we're going to write it as a ratio with a colon between the numbers. You'll see what that looks like after we do an example, but it's pretty straightforward. The idea is the odds against an event are written as the number of failures to the number of successes. And that colon that's in between, when we read that, we read it as 2. So what we have here is failures to successes. That's how we write the odds against an event. And calculating the odds against an event is not very hard to do once we know the probability. And that's the kind of problems that we're going to be looking at. Here's an example. The probability of an event is 14/19. Find the odds against this event. So our thought process here is that odds against is going to be written as failures to successes. I was given in this particular question that the probability is equal to 14/19. Well, the probability tells me, okay, well, there has to be 14 successes and there has to be 19 outcomes. Well, if I'm supposed to write odds against and I'm supposed to write failures to successes, I already know how many successes there are because it's right here. There are 14 successes. So when I write the odds against this event, it's going to be something to 14. My job that I have to do here is I have to figure out how many failures are there. Anybody have an idea? How many failures must there be? And your instinct is right, but I just want to let you tell me to give you a chance to do that. Yeah, Shelby, Nevaeh, Summer, Nadine, you're all exactly right. There are 5 of them. If there's 19 different things that could possibly happen, and we know 14 of them are successes, we'll just subtract, and there must be 5 things then that are failures. So when we go to write the odds against this event, we would say those odds against this event are 5/14. The probability is 14 out of 19, then the odds against is 5/14. A key that I want to emphasize is please make sure that Probabilities are written as fractions. Odds are not written as fractions. Odds are written as a ratio of two numbers with a colon in between them. Do you have any questions on what we did there before I have you try one? All right. The probability of an event is 4/13. Find the odds against this event. I'll make a poll for it and let you try it. So if we know the probability, find the odds. That's what we're doing in this particular question. We'll go another 15 seconds, then we'll talk about it. Let's see. All right, unanimous again. That's excellent. I'm not totally surprised in the idea that these are going extremely well, but I am pleased that these are going extremely well. That's great news that that these problems that we're working on right now are problems that aren't giving you trouble. That's really good. We'll take a look at it anyway, just to make sure. So if we know that the probability is 4/13, then we know there must be 4 successes and 13 outcomes. What we're asked to do here is find the odds against this event. Sorry, that's a, give me just a second. Okay. We need to find the odds against this event. And so that means what we need to write is failures to successes. All right, well, in the problem, I can see there are 4 successes. So I know I'm going to have something to 4, and I just need to figure out how many failures there are. There's 13 things that can happen. I take away the 4 successes. That means there must be 9 failures. And so my odds against this event are 9/4. I don't think the calculations in here will give you much trouble. Just make sure you're a little bit patient and careful. Don't go faster than you need to, because you want to make sure to write down your answer as failures to successes, and you want to make sure you write it as a ratio. Let's try another one. The odds against an event are 5/7. What's the probability? So this time you've got to go the other direction, but I'm feeling pretty good about how this is going to go. I'll set up a poll. You tell me what the probability must be if we know that the odds against this event are 5/7. We'll go another 15 seconds, then we'll talk through this one. See? Okay, first time today we're not unanimous. We have some fairly strong agreement here, not unanimous. Let's talk through this one and make sure that we're all comfortable with it. If anything happens in here that you're unsure of or is confusing at all, you just make sure to ask. All right, so we know the odds against the event are 5 to 7. So that means 5, sorry, all right, let's make sure we're functional again here. 5 is the number of failures, and 7 is the number of successes. So if we're after the probability, what we're after is successes over outcomes. And so, well, I don't know how many outcomes there are, but I know that there must be 7 successes. So 7 is going to go in my numerator. Now I just need to figure out what goes in the denominator. Well, wait a minute here. I wasn't given the number of outcomes, but if there are 5 things are failures and there are 7 things that are successes, if I want everything all together, I'm going to need to add these to find out that there are 12 outcomes. And so if there are 5 failures and 7 successes, adding those together gives me my 12 outcomes. And so the probability of this event is 7/12. Let me know if there's anything in there that doesn't make sense or is confusing or you're not sure of. The main thing is probability is successes over outcomes, and odds against are failures to successes. All right, let's talk simulations. What simulations do is they give us a way to find the probability of an event without performing the experiment or the activity that we're talking about. If I directed you to flip a coin 40 times and tell me how many heads you got and use that to tell me the probability of getting heads on that particular coin, now you might say, well, the theoretical probability would be 1 out of 2 is the probability of getting heads. And you'd be exactly right. But if we want the experimental probability, there's something we need to perform an experiment for. But I don't have a coin, so I can't flip it. Or something else that it would be inconvenient for you to actually do this experiment. Instead, what I can do is I can perform a simulation. One thing I want to do is convince you that, yes, indeed, they are valid. They're not perfect, but in some ways, neither would an experiment be, depending on what your conditions are and what it is you're doing. So we're going to treat these results as valid. And then the way that we're going to do our simulations is we're going to use what's called a random number table. We'll see an example of that. We'll talk about that in a few minutes. But basically, we're going to use a random number table to perform simulations for us that will help us find probabilities from an event or an activity that we don't want to actually do it. We're just going to use a simulation. And the way we're going to do that simulation is by using a random number table. Okay, here goes. According to the city, a certain stoplight is red 60% of the time. You're going to drive up to this stoplight 1 time per day for the next 2 weeks. Conduct a simulation to determine the probability that the light will be red when you arrive at it. Okay, so basically what I've got here is a choice to make. I could spend the next 2 weeks driving up to that stoplight once a day and writing down, is it red or not? Is it red or not? Is it red or not? Or instead of going through all that, I can perform a simulation and use that to find this probability that the light will be red when I get to it. There's a process for us for doing a simulation. And one of the key and most important things that we're going to do is we're going to assign the digits that are in our random number table. So our random number table is going to look like this, and I'll show it to you and then we'll come back to this page. We're not done here yet. A random number table is going to look like that. big, giant, random hodgepodge of digits. Now they're all one-digit numbers. That we're just looking at one digits number here. It's 851 or 85013 81010. That's not 85,013 up there in the top left. Those are just single individual digits. The reason that they're kind of grouped in fives like that is it makes it easier to pick them out when we go through doing our experiment. So the only reason for the grouping is to make them easier to read. If those little gaps weren't in there, this would be a lot harder to read. It's not easy the way it is, but that's our random number table. And what we have to do then is we have to take the digits 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. Those are all the possible digits on our random number table. We have to assign those digits. And what we want to do with that is that means when I come across a number in that table, what does it mean? Does it mean the light's red, or does it mean the light is not red? And so here, when we're assigning our digits, we want to assign some digits to mean red, and we want some digits to mean not red. And I guess we could say red, yellow, and green, but we don't have any information on yellow and green in here. So we're going to stick with red and not red. My question to you, and if you don't know or you're not comfortable with it just yet, it's okay. This is the only thing that will trip you up in simulations, I'm pretty sure, is this whole job of assigning digits. But let common sense be your guide here, because that's exactly how it works. Keeping in mind that I have 10 digits in my table, and I've been told that the light is red 60% of the time, how many of these digits do I want to give to red? If you, outstanding, Sunshine. Very good. That was fast. Very good. That's a hard idea sometimes. But okay, if that light is going to be red 60% of the time, if the light's going to be red 60% of the time, then I want 60% of my 10 digits to indicate that the light is red. And so 60% times 10, oh, well, that's 6 digits. Okay, so I want 6 digits to indicate red. So I need to have 6 of them. At this point, it doesn't matter which 6 I give to red. As long as I give 6 to red, and then by default, that means 4 of those digits are going to mean not red. But I'm going to give 6 digits to red because that corresponds with the 60% of the time that the light is red. It doesn't matter which digits I give to red. So for our purposes in this one, I'm just going to do 1 through 6 are going to be red. And that means that 7, 8, 9, and 0 mean the light's not red. Okay, got it. 1 through 6 means red. 7, 8, 9, 0 means not red. How many numbers are we supposed to look at? Well, I'm going to do this 1 time a day for the next 2 weeks. So that's 14 days. So I need to do 14 trials of this. Oh, very good, Brianna. Outstanding. I need to do 14 trials. So with this in mind, that red is 1 through 6 and not red is 7, 8, 9, 0, I'm going to go do 14 trials. I'm just going to make a little note of that over here so I don't forget. Red is 1 through 6. Not red is 7, 8, 9, 0, and I need to do 14 of these. An obvious question would be, where do I start? That's a great question. And the answer to that question is, it doesn't matter. You can start anywhere. You can just pick some number like this 9 right here. That's where I'm going to start. I don't want to influence anything with that 9 right there. So just for the heck of it, and because it's a math class, so I happen to have these around. I've got a 20-sided dice and a 10-sided dice. There in this table, there are 20 columns this way, or excuse me, 20 rows and 10 columns. So what I'm going to do is I'm going to use my I'm going to use my 20-sided dice to help me pick a row and my 10-sided dice to help me pick a column. All right, I got 5 for the row. 1, 2, 3, 4, 5. So I'm going to use this row. And for the column, I got 1. So what that means is when I do this simulation, I'm going to start right here in the 5th row, the 1st column. Okay, great. When you do a simulation, you can start anywhere. And you don't have to go through anything as formal as I just did. I just wanted to do it to emphasize the idea that it doesn't matter where you start. And I'm starting with the first number in that row and column. If you wanted to start on the 3rd one, you could. Doesn't matter where you start. The table's random. Our results should be random. And where Summer might be going right now, yes, if you need the random number table, I'll make sure you're given it. You won't have to write this down, I promise. On a quiz, you can get it from here, but and it should be in the notes. I'll check that just like I did the other. But if you need it, you'll have it available. Definitely on an exam. One thing that I want to point out, because I might start in a different place than Summer or Brianna or Sunshine. We might not get the exact same results here. So as far as the results of our experiment go, the probability that the light's going to be red based on our simulation, we may not get the same probability as our answer. That's okay. What this is about is how you can set it up and understanding how a simulation works more than the actual results that you get. Now, we are going to go through it to see the actual results that we get. And so I think I want to keep track of my results here as I do this. So what I'm going to do is I'm just going to set myself up a little place to make tally marks, because I have to do this for 14 days. So I'm going to have my red and not red. And we were starting here. And the first number I see is that 3 right there. Well, I said that the numbers 1 through 6 meant red. So that means I drove up to the light and it was red. There's my first trial. The second number is a 3. 1 through 6 mean red. So that 3 means red. So the second time I drove up to the light, it's red. Hey, I'm saving tons of time already. This would have taken me 2 days to drive up to that stoplight. I've done it in that long because I'm doing a simulation instead. Now, my pen strokes are a little bit thick right there. Okay, the next one is an 8, and 7, 8, 9, 10 is not red. The next one's a 0, so that's not red. If any of these, as I make these tally marks, don't make sense to you, you let me know. The next one's an 8, that's not red. 7, not red. 7, not red. 3 is red. 9, not red. 4 is red. See, how many is that? That's 6 and 4. I'm at 10, so I have 4 more to go. 5 is red. 3 is red. 6 is red. 7 is not red. And that's my 14. I've done 14 trials. The question said, what's the probability the light's going to be red? So here I have 14 outcomes. I have 7 successes. So the probability the light's going to be red is 7 out of 14. Based on my simulation, the probability that the light's going to be red is 7 out of 14. The main thing I want you to get from this is how setting up a simulation works, how running it can be a fairly efficient process compared to spending 2 weeks driving up to the stoplight. Every is a big word, Shelby, but yeah, we have to know. In general, I'm hesitant to say yes to a question that is always or every, but yeah, these digits on here, we're going to have to know what they represent. Otherwise, when we go through them and we go from 3 to 3 to 8 to 0 to 8, unless we establish up front what those numbers mean, then we don't know what happened with our simulation as we went through the different trials. I hope that makes sense. If not, you can ask it ask it again, and I'll try to phrase it in a better way. Oh, gotcha. No, that's a really good question, Shelby. That is a great point. The 14 here is that's how many trials we have to do. That's how many numbers we have to look at. But it's important to note that as we look at the digits here, it's just a one digit number. So the only digits we have are 1, 2, 3, 4, 5, 6, 7, 8, 9, and 0. It's these same 10 digits that we're going to have to assign every single time. That's an excellent point that you bring up. So it's these same 10 digits that we're going to assign every single time, and the number of trials lets us know how many numbers we actually look at. Very good. That's excellent. Okay. Some notes about the random number table. Now, I've provided one that we're going to use, and it's in the modules for this week because you'll need it for the simulations I'm going to ask you to work on. And the one you have but they should be completely random. There shouldn't be any like definitive patterns or anything like that. They should just be random. Now that AI is brand new, it wouldn't be hard to make one, I'm sure. They don't necessarily have 10% of each number. What I mean by that is that as we look at this random number table, it doesn't necessarily have 10% are zeros, 10% are ones, 10% are twos, 10% of threes. It's not set up that way. They're just random. This would be generated by a computer, and it just spits out a random number. You use a random number generator, and it spits them out. It doesn't keep track of how many of each number there are. By a strange coincidence, it could have 10% of each number, but it doesn't have to. And then it shouldn't have any set patterns like 1, 1, 1, 1, 1, 2, 2, 2, 2, 2. That would kind of take away from the random. So those are some sort of properties of a random number table. It should be random. It doesn't necessarily have to have 10% of each number. You could have a whole bunch of nines on there, for example, just the way this one turned out. And then as far as set patterns go, we're not looking for that. We're not looking for 1, 2, 3, 4, 5, 6, 7, 8, 9, 0 over and over again. That wouldn't be random. Let's look at another situation. A baseball player has a batting average of 300, which means he gets a hit 30% of the time. We are going to conduct a simulation to determine the number of times he gets a hit in his next 11 at-bats. What I want you to do with this poll is we're going to do the assign the digits part, and I want you to, and I'm making a poll, tell me how many digits we're going to give to him getting a hit. For some students, this whole idea of simulations it comes really easily. And it's like, oh yeah, I totally get this. For others, it doesn't. And if this is a little bit challenging for you, that is okay. We're going to practice them. We'll talk about them. You can ask questions. I want it to get to where it's like, okay, I got this. This is very comfortable. And that doesn't happen for everybody right away. I do think the assigning digits part is probably the most challenging. Because if you can assign the digits correctly, I guess if you can assign the correct number of digits to each outcome, then performing the simulation is really just a matter of keeping good tally marks, We'll go another 15 seconds on this, and then we'll talk through it. All right, let's see how we did. Unanimous. All right, that's great news. Okay, very good. So I won't spend a ton of time on this then, since it seems like we're in a pretty good place. But just to make sure, I'm going to go ahead and talk about what it is we've got here. Batting average of 300 means that 30% of the time he's going to get a hit. So what that means for us is that we want 30% of our 10 digits to represent hit. And 30% of our 10 digits is going to be 3 of them. So 3 of our 10 digits are going to represent hit. What that means is that the other 7 digits means he does not get a hit. Now we can decide on how we want to assign these. It doesn't really matter. I might just do 1, 2, 3 for hit, and then 4 through 9 with the 0 for not a hit. If somebody wanted to say, I don't like that 0 hanging out there, I want to use 0 through 2 for hit, and then just 3 for 9 for not hit. Okay, that's totally fine. As long as you set this up ahead of time and make sure that you give 3 digits to hit, 7 digits to not hit, you're going to be fine. We'll go ahead and look at our simulation here. We wanted to do 11 at bats. Yeah. So let's see. Hit, I said, was 1 through 3, and no hit was 4 through 9 and 0, and I did do 11 at bats. Last time I rolled the dice to get a place to start. This time I'm just going to sort of pick somewhere at random. I'm going to pick this 2 right here. You know, just for the heck of it, that's where I'm starting. When you decide where you're starting, what you do is you just go left to right, and then if you happen to roll over to the next line, you just start at the beginning and keep going left to right. So that's how that works. If you need to, you know, keep doing trials, keep doing trials. Or if you decided you wanted to start like right here at this 3 and you're going to get to the end of the line, then what? You just start on the next line, go in the same direction. So that's how you'll perform your simulation based on that. For no reason at all, I picked that 2 right there, and we're going to have hits and no hit. I don't know what happens if he doesn't get a hit, but we don't need to be concerned with that. We just want to know how many hits he's going to get. And so let's see, it's a 2, so that's a hit, then a 0, then a 4, then a 3, then a 4, then a 2, then a 0, then a 2, then a 4, then a 6, and then a 0. Okay, so for these particular, am I at 11? Yeah, I'm at 11. For these particular 11 at bats, there were 11 at bats, he got 4 hits. So according to my simulation that I just ran, the probability he's going to get a hit is 4 out of 11. Let me know if you've seen anything up to this point that is confusing, doesn't make sense. There's any aspect of this whole simulation process that's uncomfortable. Okay, let's look at a different one. This is a little different of a setup. A family wants to have 3 children. Run a simulation 6 times to find the probability that they will get exactly 1 boy. So this one would be really hard to do in practice. We'd have to wait forever, but instead we can run a simulation. And we're going to run this simulation 6 times. We need to assign our digits. Let's see here. So how many digits should I give to boy? And you can just tell me, I don't do a poll or anything. How many digits to boy? Not based on anything from the problem, just based on historical percentages. Great, sunshine. 5 go to boy, 5 go to girl. Now, as far as which 5, it doesn't matter. You could do even numbers for boy and odd numbers for girl. That might be hard for me to keep track of, is evens and odds, but you could absolutely do it that way. I think what I might do for this one is maybe do 1 through 5 for boy and then 6 through 9 with 0 for girl. What's different about this one is they're going to have 3 children. So what we're going to do when we look at our random number table is we are going to look at our trials in groups of 3. And you'll see what that means as we go look at it. So we're going to look at our trials in groups of 3, and then we're going to run the simulation 6 times. And then when that's all said and done, we're going to come back and say, okay, what was the probability of getting exactly 1 boy? No more, no less. The key here, what makes this simulation a little bit different than the others is because they're having 3 children, we're going to look at our results in groups of 3. All right, so let's go to our random number table. I said boy was 1 through 5, and girl was 6 through 9 and 0. And we're going to do 6 trials of 3 kids. All right, so let's see. I'm going to go to the random way to start again. I got 17, so 20, 19, 18, so 17. That's my row. And then again with the 1. All right. So what I meant by looking at these in groups of 3 is I'm going to look at these first 3 numbers right here at one time. That's my first trial, is those 3 numbers together. It's 9, 9, 9. So that first trial there is girl, girl, girl. Because I'm looking at they're going to have 3 kids, what's the probability of getting exactly 1 boy in there? I need to do a simulation where they have 3 kids. Now you could look at it as 9, then 9, then 9, and stop and say, okay, that's their first 3 kids. But I think because they're having 3 kids, we can group them together like this. And I got 0, 0, 6. And that's girl, girl, girl. Okay, and then for my next one, let's see, that's 2, 1, 2. So that's boy, boy, boy. And I need to do this 6 times, so I'll just keep going until I have 6 of them. The next one is 1, 8, 7. Okay, so that's boy, girl, girl. And then my next one is going to be 6, 5, 3. So that's a girl, a boy, and a boy. 1 more to go. And this last one is 4, 3, 1. So that's boy, boy, boy. All right, so I've got my 6 trials. And what's different about this is I did groups of 3 because I was having 3 kids. Pretty sure there's a simulation where you're flipping heads and tails and you're doing 4 flips. And so you want to look at yours in groups of 4. Same thing as we did here. Now the question is, all right, if they have 3 children, what's the probability they'll have exactly 1 boy? So I want the probability of exactly 1 boy. We did 6 trials, so my number of outcomes is 6. Now I just have to go over here and figure out, okay, where do I have exactly 1 boy? No more, no less. That's all girls, so that's no good. That's all girls, that's no good. That's 3 boys, that's no good. Boy, girl, girl, yep, there's 1. Girl, boy, boy, that's 2 boys, and that's all boys. So it looks like the probability of getting exactly 1 boy for this particular simulation, there was 1 success and 6 outcomes, so that probability was 1/6. A little bit different than the others, but the primary philosophy is the same. I think the simulations are just kind of fun to play with because there's not necessarily a correct answer, because if I would have started, I don't know, over here instead, then I might have gotten a different probability. So there can't really be a correct answer for the probability we get at the end of this. It's more about the process. And my questions related to random number tables will be more about the process.